Hello, everybody. So I'm Victor. Thank you for the introduction. Today I'm going to talk about Drammer, about the Rawhammer attack on Android, and in particular I'm going to talk about the making of. So I'm going to explain you how we actually pull off this Drammer attack. So Drammer routing Android phones with Rawhammer, but the question, of course, would be why do we care about making of, right? So I think it's going to be fun to talk about this. It will show you some insight in the academic thought process that we had. I'm going to show you some new interesting Rawhammer techniques. And although we couldn't use these techniques in the final paper, they're so-called negative results, and negative results are still results, so it might be interesting to look at this. A disclaimer before we start: this presentation will be technical. It will be about me, so if you don't like me, you can still move to the other track. And there might be some strong language in the slides. I will try to keep it to a minimum. But if you're easily offended, maybe track 2 is also interesting. Okay, a little background before we start. Who am I? I'm a PhD candidate, as I said before, at VUSEC. VUSEC is the system security group in Amsterdam at the Vrije Universiteit. We have a very cool webpage that you really should check out. But let's look at who actually is in the group, because there are important people here for the Drammer talk. So of course, does it work? That's me. Then this here is Herbert Bas. He's the professor of our group. He's really the boss. And then next to him is the mastermind. That's Cristiano Giuffrida. He was very involved in this project. But also this guy over here, is Gave Rajavi, was very much involved. And then there's also Ben, who's also going to be on the slides next. So a little bit more about me. I'm a PhD candidate, and my project is funded by a collaboration between the US and the Netherlands. And this means that I'm collaborating with the University in Santa Barbara about Android malware. It's very generic, but we try to do some research on Android malware. And I started in June 2014, so I should be ready next summer. And then for this talk, for Drammer, the important dates are somewhere last year, between February and the end of May. So let's look at them. February 18, there was a deadline for Usenik Security, one of the scientific security venues that we were submitting to. Then 6 days later, I would present another paper, an Android issue at Financial Crypto in Barbados. A couple months later, the end of May, we had a paper accepted at Security and Privacy, and also another scientific venue. And then 2 days later would be the deadline for CCS. And CCS was what we're targeting with our work. And then the idea was that between March and May, I would go to Santa Barbara, visit the university lab, the lab there, and do a project on Android malware. Okay, so let's start with the introduction. Before February 18, there was this Usenik security paper deadline. I was working on another paper, in-depth analysis of disassembly of x86 and 64-bit binaries. I was taking care of all the hotel reservations, flight reservations, and housing for both Barbados and Santa Barbara. And I was watching Ben and Gave. And actually, I was watching how Ben and Gave were breaking the internet with FlipFeng3. And I hope that you are sort of familiar with FlipFeng3. I will briefly talk about it. It's cross-VM exploitation with Rawhammer and memory deduplication. Is anyone here not familiar with Rawhammer? You can see hands. So, one. Okay, so you all know about Drammer. So let me briefly go over this then. You have these memory cells, capacitors that store a 1 or a 0 by storing a charge. And these cells have a discharge rate. So that's why we need to refresh our DRAM every 64 milliseconds. And now people found that you activate neighboring cells very frequently, you can increase the discharge rate, and you end up with Rawhammer. So we have a victim cell that represents a 1, and then you access neighboring cells very, very frequently, and then at some point the victim cell, the charge is leaking this below some threshold, and the 1 becomes a 0. So an image, DRAM is a matrix of cells, so you access one row and many times, and you see that a neighboring cell discharge is leaking, and the one flips into a 0, so you have a bit flip. Now, these rows that we're reading from are called the aggressor row, and the row in which we flip a bit is a victim row. Now, for Rohammer, it's important to understand that not every bit may flip. You sometimes 0 bits flip. But once you have a bit flip, very often you can reproduce it. Now, people did some more research on this, and they found that you can also do double-sided Rohammer, where you sandwich a victim cell with 2 aggressor rows. And this would increase the chance of flipping a bit. But doing this so-called double-sided Rohammer is a bit harder. So the challenges for an attacker, if you're an attacker, if you want to do this, there are basically 2 things you need to do. First is you need to bypass the CPU, and second is you need a way to select the right addresses. So let's briefly look at that. Bypassing the CPU, we all know that the DRAM is quite slow, which is why whenever the CPU is reading some data from DRAM, it will store it into a cache. But if we are going to Rohammer, we must read the same value from DRAM many times. So we need to bypass the CPU cache. One solution that many people are using is a cache flush. It's basically one instruction, CU flush on the x86 platform, where you tell the CPU explicitly, please remove this data from the cache so that next time I read it, the read will go through to DRAM. Another solution is cache eviction, where you basically read more and more values from DRAM into your cache until at some point you evict the aggressor rows from your cache, so that when you read those again, you will go to DRAM again. The second challenge, selecting the aggressor rows. For this, you should know that DRAM is working with physical memory addresses, but of course software is working with virtual addresses. And this mapping from virtual addresses to physical addresses is unpredictable. And the question is now, how do we figure out from which virtual addresses in our program we should read from to make sure that we're reading from the correct aggressor rows? So one solution is just don't, and then you end up doing single-sided Rohammer. If your DRAM is buggy enough, this will still work. But we found that on Android or on ARM, this is not really the case. So the real solutions are using either PageMap, which is a special file that just holds this mapping. So you open the file and you look up the virtual address and you get a physical address. Or you can use so-called huge pages. And these are virtual allocations that are mapped to physically contiguous memory. And if you have huge pages, then you can simply use relative offsetting to select the aggressor rows. So with this, you can do Rohammer exploitation. There are 3 steps involved, usually. First is you do memory templating, which means scanning DRAM for bit flips that you can use. Then you have to land some sensitive data in your DRAM, some data that you want to flip a bit in. And this data must be stored at this address in DRAM that is vulnerable to Rohammer. And then you reproduce the bit flip, you modify the sensitive data, and you compromise the system. This is what we call a flip-fang shui attack. Okay, so go back to me watching Kaveh and Ben breaking the internet. So this is Kaveh on the left and Ben on the right, presenting their work at Black Hat Europe last October, or I think. And basically what they're doing is they're breaking the cloud with Rohammer. So in the cloud you have a victim and you have an attacker, their attack model, that share the same hardware. So they're both on the physical hardware with 2 separate VMs. The attacker is root, of course, in his own VM, so he can use all the nice tricks to do cache flushing and to use huge pages to figure out where memory he should read from. So then what they did in this paper, they do 2 attacks, which I think are both really cool. One is they flip a bit in a RSA key that is used for SSH in your authorized keys files. Because if you flip a bit in such key, then you're changing the public-private key pair. So if you know a little bit about RSA, you just know that it's working because you have these very two big prime numbers that you multiply with each other, and then it's very hard to go back from this very big number back to the prime numbers again. But if you flip a bit in this big number, it suddenly becomes very easy to do so. So the attacker can then factorize this new public key in which he flipped a bit, and compute the private key that belongs to this, and then use this to get SSH access to the victim VM. A second attack they did was not only flipping a bit in a cryptographic key, but also flipping a bit in a domain name. So what they did, for example, is flipping a bit in ubuntu.com, so that it becomes ubuntu.com, and then the attacker would register ubuntu.com, so that whenever the victim would do an apt-get upgrade on his machine, he would no longer connect to Ubuntu, but to Ubuntu, and pull the ls or core utils or whatever packages the attacker want to backdoor from there. So main part, Drammer. So I was looking at these guys at VU working on this flip feng shui attack, and I thought, yeah, this is really cool, right? So a couple days before this deadline that they were working on, I opened my chat and I was asking Kabe, can you not do Rawhammer on Android? Because that would be really cool. So you have all these nice tricks that you're using with memory deduplication. Why is nobody looking at Android? So Kabe's response was, yeah, depends a little bit on the speed of Android or the ARM device that we're using, but we should do some testing. It might be interesting. So I did some Google research, of course, as an academic. So I found a tweet from 2015, that was the year before, from Dan Kaminsky, and he was asking the public, does ARM have something like seal flush? And then two interesting replies were there. One was from Alex saying, yes, but it's privileged because ARM are not idiots. Okay, fair enough. And then Halvor Flake also said, there's also the question of the memory controller speed. So maybe the memory controller on ARM devices is not fast enough to actually trigger the Roamer bug. If you search further back, you will also find in October 2014 a blog post on a post on the box.chromium.org webpage where people were asking for other instructions than seal flush to flush data from the CPU cache. And this was because of the guys from Project Zero releasing their the first Rawhammer exploit. Nevertheless, I didn't find anybody saying that they flipped bits successfully on ARM. So I sent an email to Yannick and Martina, and these are the guys in Santa Barbara that I work with, saying, yeah, these Ben and Kabe, they're really writing this cool paper, and I know that the original plan was for me to go to Santa Barbara and work on this thing, but maybe Rawhammer is also interesting to look at. So I got a reply from Yannick. Yes, I like it. No idea why people are not looking into this. So we should definitely try that. Okay, first, of course, there was Barbados. So this is me going to Barbados. And then on March 1, I arrived in Santa Barbara. And then I started to bootstrap the process. So first, of course, there was still a deadline coming up because we had a paper accepted for this SMP conference, which was called Type Armor. And there we're doing control for integrity, so it's something completely different. But I had to work on this and to make sure that the paper is very nice and people like what I see there. The deadline was March 18. I submitted 15 minutes late on March 19. Nevertheless, it was still pretty good. And meanwhile, I did some work, but not a lot. So what I did was on March 10, I compiled the Android kernel myself for an Nexus 5, and I added this support for loadable kernel modules. Because the idea was that since this seal flush, the flush instruction is privileged on ARM, the idea was to do Rawhammer first from the kernel module. Because if you're running in the kernel, you can do anything you want. Just to see whether you could flip bits at all. So here's the Nexus 5, I took a picture. March 10, I was running a custom kernel. Great. March 10, we started. Deadline for the paper that we wanted to submit, May 23. Then the next day, Kaveh was asking, can you maybe run stream first? I'm curious. So I never heard of stream. So he gave me this website. And basically, this is a benchmarking tool for DRAM bandwidth. Okay, good. Is it an ARM binary? No, of course not. So I had to compile it and I run it. I had no idea what this meant. So I just copy-pasted it and then waited for Kaveh to reply. No, it's not good. Maybe it's good enough, but ideally we would get 2 million operations per second, and right now it says 0.5. So we were already a little bit pessimistic about whether this would work at all. Okay, so continued working on the other paper until at March 23, I finally got my first actual work done on this project, because this here is the main loop in ARM assembly that I was using to flip bits, or try to flip bits in the kernel. So I told Kaveh this seems to work, right? And tomorrow I will look at porting this file called meh.cc. So what is this meh.cc? It's a piece of art, but really it's a piece of crap from the remainders of Flip Feng Shui. And actually that was then based on the code from Roman.js, which was based on Project Zero code. So many people worked on this, and it was really unstructured. But it worked. So for Flip Feng Shui, they used this, and they got bit flips with it. So the idea was to just port this to ARM and run it, see where we could flip a bit. Kaveh was saying, yeah, I have a meeting in 6 hours. So for me, I was going to bed, different time zone. I told him, yeah, if you have a meeting in 6 hours, then you have 6 hours to port your code to ARM. So, okay, sure. Can you tell me how actually I'm supposed to talk to your kernel module to do the hammering? So I explained to him how the build system worked. And then I told him, yeah, so when I wake up tomorrow, will there be bit flips? And then the answer was, I doubt it, but at least we can try. He did some more work, and then he said, no, this is wrong. It's a bit more work than I thought. Okay. A bit more about this. At some point he was asking, yeah, I get this weird output from your kernel module. It says, I got a return value of 0. What does it mean? So I'm a very good programmer, of course, and I was saying, yeah, it returns the number of cycles that were used, that it took to do the hammering. So if you get 0 cycles, it doesn't look good, right? And I said, yeah, sometimes it returns 0. I don't know why, but sometimes also returns a larger value. Okay. Anyway, I already came to the conclusion that doing this kind of research was really tricky because we could do something wrong. Maybe we were unlucky with the phones, that we were looking at devices that did not have bit flips, or maybe the memory controller was really too slow. So there was a lot of things that could go wrong doing this research. Anyway, I continue looking into this problem of the 0 return value. I was looking at this piece of code, and I was saying, yeah, it's writing this value 98, but this instruction that I was using, MCR, should get the cycle count into the register R3. What is this, right? Now, why I don't really like ARM, because I figured out what was going on here, telling Kaveh this. So we have this instruction on ARM, it's called MCR, that does something with a coprocessor. Coprocessor is a generic word here. But then you have another instruction that also does something with a coprocessor, and this instruction is, anyone who knows? So it's MRC. And then the difference is that one is reading and the other one is writing. So if you have a typo in your assembly code, it was very hard to spot the issue there. Anyway, Kaveh's response was, yeah, I always thought that ARM, we never looked at this before, but I thought it was supposed to be nicer than x86, but turned out it wasn't really. Anyway, we continued trying to hammer. So it was running at some point, and then all you have to do with Drammer is you wait until you hope that you get a bit flip. I was already pessimistic, probably won't see anything. Kaveh was very optimistic, and yeah, tomorrow we will get bit flips. So the next day, debugging, hammering, 4:10 in the afternoon, no bit flips. A couple hours later, still no bit flips. I don't trust this. Later in the evening, still no bit flips. Kaveh had a very good point. If it would have been easy, then people would have done this before and they would have reported it already, right? So it's not supposed to be easy, it's not supposed to work just like that. Anyway, I received an email from the boss, Herbert boss, my professor, and he was saying, yeah, Victor is at Santa Barbara, he's looking for bit flips. He is not allowed to go surfing or do anything else kind of fun until he gets a flip, March 25. Okay, so we have to flip some bits. It was in the morning. Please wake up. Must be wrong, right? So I found something, but didn't really look right. I said, yeah, must be wrong. Of course, yeah, 0 does not really look like a bit flip, but could be that the porting, something went wrong there, so maybe there's a bug in the code. So copy-pasted a bit more data, and it's weird, right? Because, so if you look at the output here, it's saying it's a bit flip in row 254, but here it's saying it's hammering the rows 2147, 2148, 2149, so it's hammering this row. So it's weird, weird stuff in the output. What do you think? Kaveh was taking a dump. Okay. But it's weird. So it's probably an issue with big Indian, little Indian, I don't know, 64-bit on 32-bit code. I don't care, right? Is it a bit flip or not, or likely? Likely, okay, interesting. We have to test again, fixing the code. So retrying, and then the next day, after I got the email from Herbert Boss, all I replied was literally this. So I found a bit flip, and then I said, I go to the beach now. So I went to the beach. And basically from there on, we knew that, okay, we can flip bits on ARM. So it's an interesting result already. Of course, it's not really enough to do scientific work on, but we know that something was possible. Over the next period, so now we're at March 27 to April 27, the next month or so, we were going into a downward spiral. Because flipping a bit from a kernel module, so it's cool, but it's pretty useless because you have to be in the kernel already, and it's pretty hard for an attacker to do so. So the next goal was for our work to flip a bit as root, but without the kernel module. So here's the process report, all the things I did during this next 4 weeks. First I did figuring out the row size, so figuring out exactly whether we're doing double-sided row hammer or not. I made changes and fixes to this mad.cc piece of crap. I found bit flips on my own phone, very cool, but also still useless. I was hammering a 64-bit device, Nexus 5X, which has a user space cache flush instruction, so I figured, yeah, maybe we could use that. I was hammering using multiple cores, because yeah, if you do it faster, then maybe you get higher chance of flipping a bit. I was playing with memory fences. I was looking at ARM performance counters. It was really a mess. And then I also got a parking ticket. There's my parking ticket. So it says parked wrong way on street. And apparently, if you're in the US and if you're in your street and you want to park, then your car must also be facing the way that you're driving. So you're not allowed, if there's a space over there, you're not allowed to just slide in and park your car. I don't really get why, but I got a parking ticket. Anyway, the downward spiral started. So I figured maybe I should look at some side channels, figure out what the hardware is actually doing. So that's next. First thing I did is reading from 2 different arises and then measuring how long it took me to read these values from the system. And what you see here is that there's a spike close to 64 bytes, which means that the level 1 cache was 64 bytes. There's another spike over here that would tell me that level 2 cache was 128 bytes. So, sorry, I'm not saying this right. So the cache lines are 64 bytes for level 1, and for level 2 it was 128 bytes. I did more side channels, more reading, and here I found that the level 1 cache actually is exactly 16 kilobyte. I found that the level 2 cache is 2 megabyte, using another cool side channel. But all of this you can just find on Wikipedia. So it was a bit useless, but at least I knew that I was using the correct data. But basically what we have here is side channels and more side channels. Okay, I got a message from Kave. Ben, the other guy who did Flip Feng Shui, is also looking at flushing the cache. Maybe you should work together. Although he's only doing it for the purpose of money, so he was looking at iPhone. But he had an idea to do cache flush system call that might actually work. Yeah, sure, I also want to make some cache. So let's look at this. The cache flush system call. So we open the man page, and apparently every Linux system has this system call. And if you look at the description, it says flush the contents of an instruction or the data cache. Okay, so the idea now would be, since you can call this system call from user space, would be to hammer in user land and then call this system call, the cache flush system call, to flush the cache. However, if you're jumping into the kernel after every read, this is going to be very expensive, and you're going to be too slow to actually trigger this row hammer bug. But what if we can? What if we don't have to flush after every single read, but what if you flush after a number of reads? So this is what we call pointer chasing, or something similar technique. We have here the DRAM on top. We have 3 rows, and we have the CPU cache. So and what we're doing here was reading from the first row, the first offset, 1 cache line exactly, would get stored in the CPU cache. We would read from the third row, offset 0, would be stored in the CPU cache, different cache line. We would go back to the first row, read again, stored in the cache, go to the third row again, etc., until we read all the cache lines that are available, and then we do cache flush. So now we only have to do a cache flush for every 6 reads, instead of after every single read. So we flush the cache, and then we loop back and read again. So here you only have to pay for every n accesses, where n is arbitrary or not entirely arbitrary, so there's an upper bound to this. But you're paying less for the kernel overhead introduced by cache flush. But does it work, right? Can we flip bits with this? Well, turns out we can. We wrote our own cache flush system call implementation, just to make sure that it was really doing what we wanted it to do. And I implemented this, and it was really working. I was flipping bits, so it's cool stuff. But when I was using the cache flush system call that was provided by the Linux system, it didn't work. So yeah, we have to read the menu. Okay, so I read the menu. And then there was a bit more near the bottom of the man page, where it says, so you can the cache maybe that you're flushing, maybe one of iCache or dcache. And then the dcache was saying, write back to memory and invalidate the affected cache lines. But what is invalidate? What does it mean? And why does it not say flush? So if we then look at iCache, for example, it says flush the instruction cache, flush the cache. So can we use this? In other words, can we use a different cache? So previously, we were reading only from DRAM, and the data was stored in the cache, but more particularly, it was stored in the dcache, the data cache, the specific CPU cache where you store data from memory. Now we're going to try to do the same trick, but get these cache lines, these memories stored in the iCache, so the instruction cache. So what we're going to do is a really nice trick. we're going to flip bits by executing code. So in DRAM, we have this region that's executable, and in the first cache line of the DRAM, we have an instruction jump plus 6, so 6 offsets away. And what is there 6 offsets away? So first of all, it's of course 2 rows away, and then there we find another jump instruction that just go back 5 offsets. So we're going back to the first row again. There's another jump, come to the third row, come back to the first row, and then near the end, in the last set of instructions, there will be a combination of cache flush, so flush now the instruction cache, and then jump back to the beginning. So we're flushing the cache, and we're jumping back. So we're executing code and trying to flip bits using this. And it worked. It's pretty cool. So we were using our own cache flush system call implementation again, and we were flipping bits by executing code. And if you know that this works, now you can do things like rowhammer-oriented programming, where if your gadgets are right enough, then maybe you can stitch the gadgets in such a way that you're doing a rowhammer attack. Cool stuff, but of course, it didn't work when we were using the cache flush system call that was provided by the system. So, why? Maybe the cache flush system call is bloated. Maybe there are too many instructions in there, adding too much overhead. So yeah, let's read the manual and also let's look at the code. So I did that, and then I was running into page 1496 of the ARM v7-A manual, and I found this nice table with cache maintenance operations. And this instruction below is the instruction that I was using in my own implementation. So this one was working. MCR P15 says send this command to coprocessor 15. R4 would be holding the virtual address, or the address that I wanted to flush. And if you look up the other values in this table, you will see that I was using this instruction DCIMVAC, data cache invalidate by MVA. This was working. Okay, so let's look at how Linux implements this cache flush. It's actually, the system call is implemented in the traps.c file. It calls the doCache operation function, which is calling flush cache user range. And then this is actually implemented in this function, which is in another file, and then you end up with an entry here, which is purely assembly code. And the interesting bits here are 2 MCR instructions. So let's copy paste them and look here. Where do they map to? So they were mapping to the data cache clean by MVA and the instruction cache invalidate by MVA. And when I copy pasted this code, implemented it myself, and this didn't work. But as soon as I would change these operations to use the green one, then I did find the bit flips. So why is this? The difference here between the red bars and the green bar is this field, POU, point of unification, and point of coherence. So anyone here who ever heard of point of unification versus point of coherence? Which is very good, because then I'm not the only one. Read the manual. So I did that. And then it turns out that on ARM, this point of coherence, I looked it up, and it is the point at which all observers are guaranteed to see the same copy of a memory location. And typically, this is the main external system memory, so DRAM. So point of unification is the point of unification for a core is blah, blah. For example, a unified level 2 cache would be the point of unification. Okay, so I was using POC, which was working, but as soon as you switch to POU, it's not working. So basically what we're doing here is, if we're going to invalidate the POU to the POU, point of unification, we're flushing the CPU cache. And then we're reading back from the shared level 2 cache. So we only flag level 1, level 2 stays the same. So the reads that we were doing using this technique, they were not going to DRAM, so we were really indeed not flipping the bits. This gets loaded back into the CPU. Well, if you're evaluating to POCs or point of coherence, it's of course clear now. You flush the CPU cache, and then also the level 2 cache is flushed, and then you read back from memory back to the core 0. So back into L2, and then back to L1. Okay, so I tried all of this, cool stuff, didn't work. So April 26, it was a little bit less than a month before this deadline that we set to ourselves. Some bad news, right? So trying everything, it didn't work. What's left is still to look at this, cache eviction sets, turns out also didn't work, or DMA, direct memory access. The first one doesn't look good either. And actually, I was saying, we're almost at the point, because the deadline was coming so close, and we really wanted to write something, to submit a paper to this conference. We were considering to write a paper about why Johnny cannot flip bits on ARM, because it was really turned out to be almost impossible to do this. Until Martina replied, yeah, this Ion, Android Ion, might be interesting. So it provides large, physically contiguous buffers. So physical contiguous is good, so we can do double-threaded Drammer. And you can allocate them from user space, and they have their own caching policies. So it looks like everything is there. Can you see if one of the test phones I was using has this dev Ion interface? Yeah, it was there. Sounds interesting indeed. So let's look a little bit at DMA, bypassing the CPU cache. So, because this is the really big issue that we're fighting, right? Sometimes the CPU caches are undesired. So sometimes you don't want data to get stored in the CPU cache. For example, if you have another device on your phone, for example, GPU, could be an audio device, could be anything, that's doing operations on the memory that the CPU is also working on. And in this scenario, you don't want data to get stored in the CPU cache, because then the CPU will be working on something different, older or newer than the GPU is seeing. So every operating system must provide a form of DMA, direct memory access. And as it turned out that these devices, for example the GPU, might be stupid. And if they are simple enough, they cannot translate virtual to physical addresses, mappings. And then this memory that you're sharing with the device, so this DMA memory, has to be contiguous in order for the device to work with it. So if you have this, then DMA is very much acting like a huge space that we saw before. So I looked at Ion, did some research. I told Gabe, yeah, this Ion, this might be the place where we can find flips. Ion, what's this? Canon? Ion Canon? I don't know. But seriously, so the problem now was that if we find bit slips in Ion, then we still have a lot of work to do, because we also wanted to do an exploit and everything, before the deadline of this paper. So really, we're going to have an issue, because also I was there with the family and I had to travel, right? So you're in California, you should see the main viewpoint. So I was going to LA for some days. I had to go to San Francisco for this conference. I had to make a presentation for that. I had to do whale watching. It was pretty crazy. Anyway, I briefly looked at Ion, and then 1 hour later, I said, yes, here it is. We can now flip bits in user space using this Ion memory allocator from Android. Okay, he was happy. What is this? Eviction strategy? No, I was not looking at this guy. It's DMA. A couple days later, we had a flash meeting at the University of Santa Barbara, and there was a certain professor who was saying, very enthusiastic, okay, so you found the right library. Congratulations. Yeah. But really, he was right. Because what do we have so far? So we showed that we can flip bits on ARM. What we can do, we can analyze a bunch of phones and then say how vulnerable they are. And then at best, we can port the Google Project Zero exploit. Which, yeah, it's fun, but it's not really groundbreaking scientific research. So it's only a port. So we need something better, right? We don't have memory deduplication. We found that because it turned out many devices have memory deduplication disabled, and Android actually disables this by default because it's too expensive. So Cristiano from VU, he had a plan to do some kind of exploitation that would be deterministic. And they had a meeting, a VU meeting. I was sleeping, and then I got this. Dude, you screwed. We came up with a possible attack with Ion, but Eric was involved. So you can imagine how complicated it got. And this is Eric Bosman. So my reaction was no. If Eric is in, then I'm out, I'm over, it's over for me, I cannot really compete with this guy. Kevin was saying, yeah, finally you're doing cool enough stuff for Eric to come in. No man, I'm out, I'm gonna drink a Corona. So I had a Corona. But, so this Eric Bosman guy, he's super smart. He did the SIG return-oriented programming, which won an award at Security and Privacy, and then later, last year, he did memory deduplication with Drammer to break ads, which rewarded him a pony. So really good guy. Anyway, I received a photo of what they talked about. Your next few weeks. So it was looking very good. Then we had a Skype call, and it looked much better. Anyway, this was the attack that I had to implement. So what we have to do is land sensitive data. So let's briefly talk about the threat model. So we have a recent Android operating system, no memory deduplication, and we're going to assume an unprivileged app that wants to get root access. The goal here ultimately is, of course, to read-write to anywhere in memory, because if you have that, then you can find your own administrative kernel data structure and then override your user ID to get root. The approach, so the core of the idea was that we're going to land a page table somewhere in memory where we can flip a bit, and then we flip a bit in this entry. Okay, so a little bit about page tables. Page tables are used to map virtual addresses to physical addresses. For example, your user space program has this buffer allocated, and it's storing hello world in there. And it might be that for some reason, in physical memory, hello and world are stored at these particular locations. And then you have this mapping. So a page table now is nothing else than just a table with the virtual address and then what physical address belongs to it. I made it easy for you because I also added the binary representation here of the physical address. Now, where are these page tables stored? Of course, also in memory. Now, what if, for example, this page table is stored just between the buffer that we have allocated in our user space program? Now we can read from these two buffers and potentially flip a bit in the page table entry. What happens if you flip a bit in a page table entry? We can modify the mappings. Let's look at this example where you flip this one bit in the physical address of a page table. This is this arrow. It's pointing to hello for now. By flipping this bit, we're changing the physical address to no longer be 1400, but to be 1000. And if we then also update the pointer, it will now point to the page table. So right now we have a user space program with a buffer that was originally pointing to hello, but now it's pointing to the page table. And page tables give us read-write access to anywhere in memory because we can modify entries, so we can override existing ones, or we can add new ones and then use that to access memory. So really the goal is to get access to your own page table. But the question is, how do you get this page table stored here and not somewhere here or somewhere else in memory? And this is where basically VU, it was mostly Cristiano, Eric helped a little bit, but it was mostly Cristiano who worked out this technique that we call FIS, as in physical feng shui. So let's look at memory in the initial state of the attack. So we will go and launch the Drammer attack now. We have some allocations, some programs that are running. Then the first step is exhausting large chunks of memory. We do that, we get 2 of those, and we're going to find bit flips. We're going to hammer. So we're hammering memory until we find a bit flip. Then the second part of the exploit is exhausting rows. So smaller, medium-sized chunks of memory. And in this case, we have 3 that we are going to allocate. Step 3 of the attack is release the large chunk that has the vulnerable page in it with the bit flip. So we give it back to the system. And immediately after that, we're going to allocate smaller chunks of the size of the row size again. And since we just exhausted them in the previous step, we will now be sure that we will get the same chunks that we just released, also including the chunk that has the bit flip in it. So we exhaust them, and we get these allocations. Next is releasing the vulnerable row. So now we have more control. We can release 1 row completely. And we're also going to release larger chunks. And we do this because in the next step, we are going to allocate small chunks. And we do not want the system to get out of memory. So the next step, allocate pages. We're going to allocate pages, small pages, until we are breaking the vulnerable row with the bit flip in it into smaller chunks. And this works because the underlying memory allocator of Linux will make sure that the large chunk in the middle is used last. To make sure that if anybody else comes in and wants to continue this chunk, he will get this one. So we just allocate until we hit this vulnerable row. Then we do some padding, so we do some more small page allocations. And then in the last step, we're going to map a page table. So you can do this with map fixed and get a page table on exactly this location. From there on, we use the trick I described before, do row hammer, flip a bit, and get root access. So I was working on this mid-May, telling Cristiano, yeah, I don't really know how we're going to detect all of this, so it might be the last missing piece. So what do you mean? So I explained to him my issues for a few minutes. His reply was, yeah, super cool. By the way, are you around tomorrow? I can drive to Santa Barbara. So it turns out he was actually in California as well. So he took a car and drove to Santa Barbara. And we had a very long chat. It was a very, very productive day, actually. And this was the end result. And after this, we knew that it was going to work. We had all the building blocks, so we could continue writing the paper. One thing that was remaining in the last 6 days was doing evaluation. So I got a bunch of phones from the lab. I had a very professional setup when I was hammering all the phones. And we evaluated this. So interesting enough, we found that sometimes one of the Nexus 5 phones would have 0 bit flips, while if we look at another Nexus 5, we would actually see close to 1 million bit flips. So it's the same hardware, but still one device has no bit flips at all, and the other one has really a lot. Sometimes, because not every bit flip is exploitable, sometimes we find the first bit flip after 1 second. Sometimes it takes us 15 minutes before we get the first exploitable bit flip. We did some more measurements, and we found that once we have this first bit flip, we can do the rest of the exploitation in 22 seconds at most. So the last few days I was wrapping up, writing the evaluation. I spent some time with the family, searching for another side channel to get all of this working. Then there was the Security and Privacy Conference. We had to do paper writing, and we submitted in time, and it got accepted. After this, when I got back in Amsterdam, I still had to finish the exploit, right? So I knew it was going to work. We had all the building blocks, but we didn't have a proof of concept. So I worked on that. And also, after we had the exploit finished, we had to disclose this to Google. So when I was writing the exploit, I was mainly looking at screens like this, and I'm very lazy, so I would spot the bit flip by just looking at the screen, and then there it is. So the 8E, yeah, really. Anyway, after the POC was finished, we contacted Google and we sent them a list of mitigations that we think would be appropriate to stop this kind of attack. We contacted them on July 25. Now, why is this date important? It's important because it was 91 days before CCS, before you would actually present our work. And Google Project Zero, if they find a bug in a Google product, they will give Google 90 days to fix it. So we were very much on time with our report. Nevertheless, at some point we had a video call with them, and then they asked us, yeah, can you maybe publish at another venue later this year? Nah, we didn't do that, because we need papers, right? And then, yeah, what if we give you some money in return? What if we support you financially? Can you then maybe delay publication? Still no. Okay, then maybe can you obfuscate some part of the paper so that it becomes harder for the expert to implement your attack? Again, we didn't do it. So ultimately, we were rewarded a massive amount of $4,000 for this attack. In November, they already published some updates that would stop the attack. And then they said, we will continue working on a longer-term solution. I think this is currently in place already, so you should all be safe, assuming your vendor pushes these updates as well. Anyway, it's time for conclusion. So now what, right? So with Drammer, we sort of completed the 3 steps of exploitation vectors. So we can exploit the cloud with Rawhammer. We can exploit the browser or the desktop environment. And now we're also exploiting the mobile phone. So far, we have seen bit flips on DDR2, 3, 4 modules, but also on low power DDR2, 3, and 4 modules, the chips that are used in your mobile device. And with Drammer, we show that you don't need memory deduplication to do these kinds of Drammer attacks. You can do it without custom operating system features. You just rely on how the operating system itself is supposed to work. What is important to understand is that software really was never designed to deal with Rawhammer bit flips. Proposed defenses so far, they are still in early stages or easily bypassed. And never, even hardware mitigations that have been out so far are currently still optional. So ECC is optional, TRR, target row refresh, is optional, and we see that mobile vendors are not very keen of adding these mitigations to the hardware because it will drain the battery faster. So it's really a tough problem. And then finally, you cannot fix Rawhammer. So if you have a DRAM module that is vulnerable, you cannot open your phone, get out the DRAM chip, solder it a little bit, and then somehow fix it and then put it all back together. So there's really no fix for this. And this is why I think we need to do more research on this and try to come up with very good ways to actually stop these kind of attacks. So that's all. You can find more details about the project on our webpage. You can also find a test app that you can install. If you trust me enough, you can run this on your phone and then figure out if your device is vulnerable. I also open sourced some part of the code on GitHub, the code that allows you to search for bit flips. And of course, you can follow me on Twitter. So that's it. Thank you.
Thanks very much, Victor. We have time for a few questions, if you'd like. Anyone? Yep.
Thank you for your talk. I've got one question. You say Rohammer cannot be stopped. It's a hardware problem. What did Google do to prevent it?
Good question. Google stopped this by, so if you know a little bit about how this ion allocator works, basically there are different heaps that you can allocate memory from. And there's one special heap that's called the contiguous heap, and this gives you contiguous memory. So it's there to support these devices that are really simple and do not know how to work with these mappings. Turned out that, if I'm correct, Qualcomm, so the main supplier of Android phones these days, is not using this contiguous heap. So it was very easy for them to just disable this. So now you no longer can get contiguous memory. It complicates the attack. Yeah, it should still be possible to pull it off. But yeah.
Any other questions?
Hey, thank you for the talk, really interesting. You had one slide where the one Nexus 5 had no bit flips. Do you know why this is the case? Is it like different hardware manufacturer or?
This one, right?
Yeah, this one, exactly.
Yeah, good question. I don't know. It could be that this Rohammer issue is per batch, right? So it could be a batch of DRAM chips that might be not so good than the other ones. Could also be that there's some kind of wearing effect. So maybe if you use the phone more and more over time, it gets more likely to flip bits. But we don't really know. So actually, we should actually open these phones at some point and then look at the DRAM.
That would be really interesting because, like, I mean, if there's some manufacturers that can produce better RAM or whatever, then why not use these, right?
Yeah, it's very interesting.
Any more questions? No? Well, thank you very much, Victor.